It is my great pleasure to introduce our next speaker. Sarah Koch is an amazing mathematician. She has 2 PhDs in mathematics, one from the University of Provence and one from Cornell. After NSF postdocs at Warwick and Harvard and a Pierce Fellowship, she joined the faculty at the University of Michigan, where she's now an associate professor. She's known for her work in complex dynamics. She's an expert on Thurston's topological classification of post-critically finite rational maps and the interesting dynamical systems and correspondences on moduli space that she discovered in her thesis. That work developed into a whole line of research by itself, but she's well-versed in all sorts of interesting connections between complex dynamics and topology, and Teichmuller theory, and group theory, and number theory, and you get the idea. I first met Sarah in 2010 at a conference in Barbados on moduli spaces and the arithmetic of dynamical systems, and I remember how shocked I was and how shocked we all were to find out that she was a very recent PhD because she just seemed to know so much mathematics, so much about everything. She's an extremely creative mathematician. She does a lot of work with pictures and visualization, which I'm sure you're about to see. Lucky for her students, she's known for her devotion to them and for how much time she spends with them and on her teaching. Lucky for all of you, she's known for giving amazing and engaging talks to all kinds of audiences. Lucky for me, she's known to be an extremely enthusiastic, joyful, and generous mathematician. She shares ideas and energy with abandon. If you're lucky enough to crash at her apartment, you'll probably wake up at 3 a.m. because she's Skyping about math with one of her collaborators. And she will ask the best questions after your talk that will lead you to another paper. She's the only person I know who takes mathematical theorems, not even her own, and turns them into Christmas cards. So I'm incredibly lucky to know her, and I'm really honored to introduce her today. Here's Sarah Koch talking about what is the shape of a rational map.
Thank you very much. Oh, wow. Thank you very much, Michelle, for that awesome introduction. I am quite honored to be here. I'd like to thank the AMS and the MAA for giving me this opportunity to tell you about what I think is quite literally an extremely beautiful subject. So first, thank you all for coming. I'm going to give you a little bit of a tour of the field of complex dynamical systems with this lecture. We'll sort of bounce around a little bit. We'll start with quadratic polynomials, and then we'll move on to some other rational functions, and we'll talk a bit about parameter spaces, and I'll show you some of my favorite things. Before we get started, though, excuse me, I'd like to just make a comment about the title of my talk. I chose this title. It was inspired by a post of Bill Thurston's on Math Overflow. And the title of his question is, what are the shapes of rational functions? And I think this is a great question. And just to set the context here, Thurston's considering a rational function, which is a holomorphic map from the Riemann sphere to the Riemann sphere, or equivalently, it's a ratio of 2 complex polynomials. And he's asking some very interesting questions about it in this blog post. There are actually many, many questions that he's asking, and one kind of flavor of the kind of questions he's asking is if you fix something in the range Riemann sphere, some information like, for example, you fix the critical values of a rational function to be this list of complex numbers, what can you say about all the rational functions that have that particular set of critical values with certain combinatorics? He wanted to understand this geometrically. But I want to point out that in Thurston's questions inside this Math Overflow post, he's not identifying the domain and range of his rational function, even though they happen to be the same. He's asking questions of a non-dynamical nature. He's not iterating anything. If you exploit the fact that the domain and range of a rational function are the same, you can do dynamical systems. You can iterate your map. If you iterate your rational function, there's quite a natural candidate for what the shape of a rational function should be. So this talk is about iterating rational functions, or iterating holomorphic maps on the Riemann sphere, and studying what happens when we iterate. In fact, this is sort of, in general, what one does in complex dynamical systems. So we'll begin with the family of quadratic polynomials you see here. So I'm going to write my quadratic polynomials in the form z squared plus c, where c is a complex parameter. We should think of this as a family of polynomials parameterized by a copy of the complex plane, by a copy of the little c-plane. And as I said, we're thinking of each quadratic polynomial as giving us a function from the complex plane to itself. The domain and range coincide so we can iterate. And we're going to get some very interesting objects just by doing that. For starters, we can look at what's called the filled Julia set of the polynomial, which by definition consists of all points z in the complex plane so that the orbit, this sequence, the orbit of z is bounded. Just to look at an example, here's a picture of the filled Julia set for the polynomial z squared, which is what we get when we set c equal to 0. In black, you see the closed unit disk, which is in fact the filled Julia set of the map z squared. You can work that out by hand just from the definition using some complex analysis. In white here, you see the orbit of a particular point, this little stick figure, which I hope is visible. If you start here at this initial point and you square that complex number, you get this as the output. If you square that complex number, you'll get this as the output. If you square that complex number, you'll get this as the output, and so on. And hopefully you can see in my picture that the orbit of that point, that sequence of complex numbers, converges to 0. For this particular function, 0 is an attracting fixed point. Okay, so let's look at another example. So here is another quadratic polynomial, z squared minus 1. I've set the value of the parameter to be minus 1. And in black, you see the filled Julia set. This is much more complicated, and it's much harder to prove by hand that this is in fact what you get. This is a fractal. Okay, so this particular filled Julia set, you might notice, is symmetric with respect to reflection across the real axis, and that's because the map, z squared minus 1, has real coefficients. All right. So as before, I've indicated or drawn an orbit in white. It's a little hard to see, actually, but there's an orbit of a point. I think I started over here. You take that, you plug it into z squared minus 1, here's the output. Plug it into z squared minus 1, there's the output, so on and so forth, and you can see the orbit of this initial point converges to this cycle of period 2. This is an attracting cycle of period 2 for the map z squared minus 1. Okay. So in each of these two examples, we'll notice that the filled Julia set is in fact connected. Another example, what's the filled Julia set for z squared plus I? It's very thin. It's drawn in black as well, but there are fewer black points. It's a very thin set called a dendrite. It itself is also connected. There are no attracting periodic cycles for the map z squared plus I other than the point at infinity, which is always attracting for a polynomial. So in green in all of these pictures, you see the points that are not in the filled Julia set, which means that their orbits shoot off to infinity under iteration. Those are the green points. You can think of that as the set of points that are attracted to infinity under iteration. All right. And one more example. This is the filled Julia set for the polynomial z squared minus 2.5. It is a Cantor set. Okay, so here, the filled Julia set is disconnected and in fact, totally disconnected. And also, for this particular map, there are no attracting periodic cycles other than the fixed point at infinity for the polynomial. So just looking at this little gallery of 4 examples, you can see that as you vary the parameter c, you get very different kinds of behavior, both in terms of topology, is it connected, is it not? Or dynamics, is there an attracting periodic cycle or isn't there? What else could there possibly be? So that motivates maybe doing the following. We'll look at some pictures and try to define a natural subset in our C parameter plane coming from just our experience so far with these pictures. So here, again, we have a filled Julia set that's connected. This is one we haven't seen before. It's for some parameter C. And then over here, we have a filled Julia set that is disconnected. In fact, this one is also a Cantor set. So the natural subset to look at, or a natural subset to look at in the parameter plane, is the set of all parameters little c for which k sub c is connected. I'll call that script M suggestively. All right, so we want to keep track of where the topology changes. One very basic question is, where is it connected, where isn't it connected? All right, so we've got that subset to look at. And from the point of view of dynamics, we saw just in our examples that some of these maps can have attracting periodic cycles, but not all of them have to. So for this particular polynomial, there's an attracting cycle of some period right here. And in fact, the interior of the filled Julia set, every point in the interior of the filled Julia set will be attracted to it. Over here, we had the Phil-Julia set for z squared plus I. That very thin set doesn't have any attracting periodic cycles. So another subset that we could define in parameter space is the set of all parameters little c for which the polynomial z squared plus c has an attracting periodic cycle. I'll call that set script h. So we have two natural subsets of parameter space to study. All right. So there's our family. There are our two subsets. And there's something that's absolutely essential for understanding these sets. There's a result that goes back to the times of Fatou and Julia, almost exactly 100 years ago. It's a result, or maybe more of a philosophy in complex dynamics, and that is to understand the dynamical objects of your map. When you're iterating a rational map on the Riemann sphere, you should look at all of the critical points that you have and study their forward orbits. What the critical points of your map do under iteration will tell you a lot about the global dynamics of the map. So taking that philosophy that dates back to 100 years ago and applying it to our particular family, our quadratic polynomials, z squared plus c, have one critical point. If we think on the sphere, they also have a critical point at infinity, but the critical point at infinity is fixed. It's not doing anything. The polynomials z squared plus c have one critical point in the complex plane, and in these coordinates it's at 0. So, applying that philosophy of Fatou and Julia, if we want to understand the dynamics of our map, what we should really do is study the orbit of the critical point 0 under z squared plus c. And in fact, you can use that to great advantage, and using work of Fatou and Julia, you can prove that the set of all parameters C for which the Phil-Julia set is connected is equal to the set of all parameters C for which the critical point has bounded orbit. You can also prove, using work of Fatou and Julia, that the set of all parameters C for which the map has an attracting periodic cycle is equal to the set of parameters C for which the critical point 0 is attracted to an attracting cycle. So if the orbit of 0 does not converge to an attracting cycle, then your map has no attracting cycle. These two results are fantastic. How else could you test if a Phil-Julia set is connected? You could try to draw it on your computer, but then how can you prove rigorously whether or not your subset of the plane is connected using your computer? You can get some ideas from the picture. Or how would you know if your map does or doesn't have an attracting cycle? This is saying all you have to do is follow around the critical point. Okay, so let's sort of put this into context in terms of what we've seen so far. So these are all of the examples we've looked at. Here's the map z squared. The Phil-Julia set is the closed unit disk. The parameter 0 is going to be inside the Mandelbrot set. So we can see that the Phil-Julia set is connected, and the critical point, which is in the center of symmetry of each of these pictures, is in fact inside the Phil-Julia set. There's also an attracting periodic cycle. There's an attracting fixed point for that map. So the parameter c equals 0 is also contained in the set script h. I want to point out that just using these characterizations here, if you have a parameter c that's inside script h, that is, if the critical point is attracted to an attracting periodic cycle for the map in question, then necessarily the critical point has bounded forward orbit. So that parameter c also belongs to script m. So H is a subset of M. And in fact, we can do better. I'll make a comment about that in a second. So for these parameters, 0 belongs to M, 0 belongs to H. This map is z squared minus 1 belongs to M. The Phil-Julia set's connected. You can see the critical point, the center of symmetry, is in fact inside the Phil-Julia set. And there's an attracting cycle of period 2. The critical point is attracted to it. So that parameter minus 1 also belongs to script H. The parameter I belongs to M because the Phil-Julia set for this guy is in fact connected. I has bounded forward orbit, but there is no attracting periodic cycle. For this map, the critical point eventually lands on a repelling cycle and is not attracted to any kind of attracting cycle. Okay. Here, the critical point, the center of symmetry, this Cantor set, the critical point is shaded green, so it shoots off to infinity under iteration, which means that for this parameter, giving us this picture, that C value is not in the Mandelbrot set. Sorry, it's not in M, and it's not in H. Getting ahead of myself. Okay, and similarly, you can figure out where these parameters live. Okay, so we have two interesting subsets of parameter space that we can study. And I remarked just a few moments ago that in fact H is a subset of M, but H consists, remember, of all of those parameters for which the map F sub C has an attracting cycle. Having an attracting cycle is actually an open condition, and therefore script H is contained in the interior of script M. Okay, so what do these sets actually look like? So script M is called the connectedness locus, the set of parameters C for which K sub C is connected, and that is the Mandelbrot set. This object has been studied for about 30 years. It's been studied a lot. We know almost everything about it, but there are some fiddly little things that we cannot quite figure out. And I'll tell you about those in a moment. So in black here, you see the Mandelbrot set. This is a copy of the C parameter plane. Black is the Mandelbrot set. And every single one, well, let me just make a few remarks first about the Mandelbrot set, just to give you kind of some geography about where you are. The tip of the tail is at the parameter C equals -2. There's a cusp here. This is a heart-shaped component. There's a cusp right here at the parameter C equals 1/4. You'll notice that it's symmetric with respect to complex conjugation, and that should make sense. That should make sense because a parameter is in the Mandelbrot set if and only if the Phil-Julia set of Z squared plus C is connected. The Phil-Julia set of Z squared plus C is the complex conjugate of the Phil-Julia set of Z squared plus C bar. You just flip over the real axis. So the Phil-Julia set of Z squared plus C is connected if and only if the Phil-Julia set of Z squared plus C bar is connected, which is why this is symmetric with respect to complex conjugation. There's a theorem of Doherty and Hubbard back from the 80s, which says that, this set is itself connected. So it's parameterizing all quadratic polynomials with connected Julia sets, and it itself has that property as well. So it is connected. It is full, meaning that it doesn't have any holes in it. It has connected complement. So that's what Doherty and Hubbard proved. It is not known if the Mandelbrot set is locally connected. That's a very hard problem that's gotten a lot of attention. All right. And these components, I'm not sure if you can see them. I'm not sure if my picture is quite good enough. But if you look at the connected components of the interior, all of those components that you can see, those are connected components of H, of script H. Those are called hyperbolic components. And remember that if you're in a hyperbolic component like this one here, if the parameter moves in here, what you'll be doing is looking at maps where there's an attracting periodic cycle. And each hyperbolic component can actually be labeled with a positive integer corresponding to the period of that cycle. So here, this is the main cardioid, which consists of all parameters. The interior of this cardioid consists of all parameters, little c, for which there's an attracting fixed point. Then if you move over here, look at this, the connected component of the interior here, this consists of all parameters, little c, for which there's an attracting cycle of period 2, and so on and so forth. So you can label all of these components. Each one of these components has a positive integer. You can use these hyperbolic components to give yourself a roadmap to really lay out this picture. It's extremely well organized. And because there's only one critical point, if there is an attracting cycle, because there's only one critical point, there can be at most one attracting cycle, which means we don't have to worry about having two attracting cycles and then trying to label a hyperbolic component with two integers, one corresponding to the first cycle and one for the second. There's only one cycle because there's only one critical point. So you can really label all of these hyperbolic components with positive integers and try to study how they fit together. This picture is extremely well organized. All right. So as I said, it's unknown if the Mandelbrot set is locally connected. It's also unknown whether or not H is equal to the set of interior points of M. That's related to the question of whether or not the Mandelbrot set is locally connected. And in fact, this is the motivation or one of the big reasons why people even asked the question, is the Mandelbrot set locally connected? There's a conjecture called the density of hyperbolicity conjecture, which says, in fact, these two sets should be equal. and it's not known. A very hard problem. All right. I think we're ready to move on from here. Okay. So we have this beautiful parameter space. We have the Mandelbrot set. We have the connected components of the interior that are hyperbolic. Those are fit together very nicely. You can label them with integers. There are very special parameters or very special C values that live inside the Mandelbrot set. As we discussed, the orbit of the critical point is very important when you try to understand the dynamics of your quadratic polynomial. So instead of asking, okay, is 0 attracted to an attracting cycle, or does 0 have bounded forward orbit, you could be even sort of more restrictive. You could say, okay, I want to study the set of parameters for which 0, my critical point, has finite forward orbit. That's a very strong condition. And those quadratic polynomials that have that property are called post-critically finite. So if you look at this object here, which is called the post-critical set of the quadratic polynomial, it's the forward orbit of 0. So the polynomial is called post-critically finite if the post-critical set is finite. Post-critically finite maps are very, very special, and I'll tell you a little bit why. All right, let's just look at some examples first. This polynomial that we've seen so far, z squared minus 1, this is its Phil-Julia set. 0 is periodic of period 2. The critical point itself is periodic. This periodic cycle of period 2 is attracting and attracts all of the interior points in the Phil-Julia set. So this is an example of a post-critically finite quadratic polynomial because the orbit of 0 is finite. This is also an example of a post-critically finite quadratic polynomial. Here, the orbit of 0 is given by this diagram here. So this little 2 on this arrow is indicating that 0 is a critical point. It's mapping forward with local degree 2. So using this little diagram, I see that 0 maps to I. I, when I plug it into this polynomial, maps to minus 1 plus I. When I plug this into the polynomial, that maps to minus I, and then that maps back. So the critical point for this polynomial, the center of symmetry, the critical point maps up to I, then maps over here, then that maps down there, and then this is in a cycle of period 2. This is a repelling periodic cycle. So there are two different ways in which a quadratic polynomial can be post-critically finite. Either the critical point itself is periodic, or the critical point is eventually periodic. It has a pre-period, that is a certain number of steps, and then it lands in a periodic cycle. Post-critically finite polynomials of this sort can either have attracting cycles, and that only happens when the critical point itself is periodic, or they can only have repelling periodic cycles. And my comments I'm making are in addition to the attracting fixed point at infinity for a polynomial. Okay, so what I'm saying is every periodic cycle for this polynomial is repelling except for the super attracting fixed point at infinity. And for this polynomial, every periodic cycle is repelling except for this super attracting cycle of period 2. Super attracting just means that you have an attracting cycle that the critical point is part of. The critical point is periodic. So every periodic cycle for this map is repelling, in addition to every periodic cycle for this map is repelling except for the super attracting cycle of period 2 that contains the critical point and the super attracting fixed point at infinity. Okay, so those are two examples. We're going to see many more examples, but I'm going to need to refer to these guys a little later, so I'm going to name them. This one's called the basilica, which should remind you of this picture on a rainy day, if it reflects inside of a big pool of water in front of it. So when I say basilica, I want you to imagine that Phil-Julia set, the polynomial z squared minus 1. And then this guy over here, because it's so thin, I'm going to call this a dendrite. So when I say dendrite, I mean the Phil-Julia set of a post-critically finite polynomial where the critical point eventually maps into a repelling cycle. It's going to be connected. It's going to be very thin. Actually, that's worth a comment right there. So because one thing we can say is that if you have a post-critically finite quadratic polynomial, that means that the orbit of 0 is finite. So in particular, the orbit of 0 is bounded. So the Phil-Julia set of every post-critically finite polynomial is connected. So all of the post-critically finite parameters little c are going to be inside the Mandelbrot set. Some of them are going to be inside the hyperbolic locus, script H, where the critical point is periodic. You'll have a super attracting cycle. So for example, -1 is inside script H, I is not, but -1 and I are both inside the Mandelbrot set. So post-critically finite parameters. All right, let's try to find a couple more. So here's our parameter space, our C parameter space. As I just remarked, all of our post-critically finite parameters are going to be inside the Mandelbrot set. So here's an exercise. Find all parameters C so that 0 is periodic of period 3 for the polynomial z squared plus C. Well, we'll set this up the following way. 0 is my critical point, maps forward with local degree 2 to C. I plug C into my polynomial, I get C squared plus C back. I plug this complex number into my polynomial, and I get some expression, some polynomial expression in the parameter C, and I impose the condition that I want that to be equal to 0. The roots of this polynomial, almost, are going to give me the parameter C for which 0 is periodic of period 3, except there's one extra. The root at C equals 0 I'm going to ignore because that gives me something degenerate. So if I want to know how many quadratic polynomials are there for which 0 is periodic of period 3, I just have to find these roots. Well, there are 3 of them, and what are they? Well, 2 of them are complex conjugates, these 2, and 1 of them is real. Here, in each picture, I've outlined the orbit of the critical point. The critical point is the center of symmetry. Here you can see that it's periodic of period 3. In its complex conjugate, you can see also periodic of period 3. It's harder to see in this real picture. Now, these guys also I'm going to need to refer to later, so they have funny names as well. I'd like you to try to remember them. I'm not responsible for their names, but they're actually incredibly useful. Duodee named this Julia set the rabbit, for obvious reasons. It has 2 ears. This is called the co-rabbit, the complex conjugate. And John Milnor named this one the airplane, because it looks like an airplane flying out at you from the plane of the screen. Okay, so the rabbit, the co-rabbit, and the airplane, period 3. All right. If I asked you, okay, great, how do we find all parameters little c for which the critical point's periodic of period 4? What would you do? You would do exactly the same thing, although except instead of starting with a 3 cycle here, you'd start with a 4 cycle. You could do the same thing, okay, well let's find all parameters c for which the critical point is periodic of period 47. You start with a graph here where the period's 47, you set up the equations, and you grind through and find those parameters. This is how to find the set of C values for which 0 is periodic. The set of these parameters is very interesting. And in fact, the polynomials that generate them are also very interesting. So let's look at those. These are called Gleason polynomials, named after Andrew Gleason. We named them that because one thing that he proved, and I'm not sure if he did anything else in complex dynamics after that, but this was enough. He showed that these polynomials have simple roots. Okay, so what are these polynomials? These are the polynomials of period n. So given a period n like 3 that we just did in our computation, the Gleason polynomial of period n is a factor of this polynomial, the factor whose roots correspond to 0 being periodic of period n. Okay, so G1 is C, G2 is C plus 1, C equals -1 is a root of this polynomial, and we saw that for z squared minus 1, 0 is periodic of period 2. That was the basilica. This is the polynomial G3 that we just studied on the previous slide, whose roots correspond to the rabbit, the co-rabbit, and the airplane. There are 3 quadratic polynomials where the critical point is periodic of period 3. There are 6 quadratic polynomials where the critical point is periodic of period 4. 15 quadratic polynomials for which the critical point is periodic of period 15. And again, I know that the roots are all distinct because of Andy Gleason's lemma or proposition, which is really just computing the discriminant and showing it's not 0 mod 2. Now, one question that the number theory people always ask us, and in fact that we ask ourselves all the time, is, are these polynomials irreducible over z? I would love to know the answer to that question, and I don't. It's been checked up through period 25, maybe, with the computer, I think. Oh, I have no idea how to tackle this problem. It seems really hard. Okay. So these are the Gleason polynomials. These are the polynomials whose roots give you those parameters for which 0 is periodic of a certain period. One thing to do that's actually quite entertaining is to take all of these polynomials, this infinite collection, and plot all of the roots in the same copy of the complex plane, which is sort of visible here. You'll get a Mandelbrot set in space. So really what you get is you get this countable collection of algebraic integers. The roots of the Gleason polynomials are algebraic integers. This countably infinite collection of algebraic integers. And it follows from a theorem of Kurt-McMullen's that if you take the topological closure of this set of algebraic integers, it will contain the boundary of the Mandelbrot set, that extremely complicated fractal that we still don't completely understand. So the post-critically finite parameters are even better. The parameter C, for which 0 is periodic of some period. If you take the topological closure of that, that can see the boundary of the Mandelbrot set. So these polynomials, these roots, this algebraic data is very special from the point of view of this parameter space. All right, so there's in fact one other way in which a polynomial could be post-critically finite if it's quadratic, and that is instead of 0 being periodic, if it's eventually periodic. These are called Mizerevich polynomials, and I'm going to skip through this just a little bit. I don't want to spend too much time, but you can sort of do exactly the same thing. If I wanted to find a polynomial, a quadratic polynomial of the form z squared plus c, where 0 after 2 steps was fixed, well, then I could write down some combinatorial data and write down a polynomial in the parameter c whose roots gave me those parameters. These are called Mizerevich polynomials. These polynomials are interesting also. Their roots are algebraic integers. The roots live in the boundary of the Mandelbrot set, and they're dense in the boundary as well. And we also don't know if these polynomials are irreducible over z. That's another question. Okay, so post-critically finite parameters are pretty important. They come in 2 flavors. Either the critical point's periodic or it's strictly pre-periodic. Okay. Here's a theorem. We do know something. I guess I should sort of take back what I just said. We don't know in general if the Mizerevich polynomials are irreducible over z, but we know for a couple of families. So a graduate student at Wisconsin, Vifa Goxel, proved that for all pre-periods, for all k, that is the step that you take here, for all pre-periods, the Mizerevich polynomials mk1, which means you can take k steps here and then eventually be fixed, and mk2, you take k steps here and eventually map to a 2-cycle, that these polynomials in the parameter C are in fact irreducible. And then some co-authors and I, Xavier Bouffe and Adam Epstein and I, a couple weeks ago actually, proved that this also holds if you take k steps and then map into a 3-cycle. I have no idea how to tackle the problem in general. So this is the only thing that we know, the only thing that's known about the question of irreducibility of these polynomials. Okay, so I want to say just a word or two about quadratic rational maps. So I'm going to shift gears a little bit, moving from quadratic polynomials to quadratic rational maps. Then I'm going to show you some amazing movies, and then if I still have time, I'll circle back to quadratic rational map from the point of view of parameter space. We've just talked about quadratic polynomials and quadratic polynomial parameter space. Now let's discuss quadratic rational maps. Quadratic rational map is a ratio of 2 quadratic polynomials. You can think about this list of 6 coefficients as giving you a point in P5, that's complex projective space. Okay. So in fact, you can think of a space, the space of quadratic rational maps, as being an open subset of P5 where you have to remove the locus corresponding to all points where these 2 polynomials have a common root. Okay, so it's some open subset in there. It's quite large, but instead of studying the space of all quadratic rational functions or rational maps, we really only want to study what's called the moduli space. We want to mod out by conjugation by Mobius transformations. If we do that, the space that we end up with is isomorphic to C2. And I'll call it curly Q, the moduli space of quadratic rational functions. A point in curly Q is a conformal conjugacy class of rational functions of degree 2. Okay. So how do we understand this moduli space? It's complex two-dimensional. That's a lot harder to visualize than my beautiful copy of the complex plane that parameterized z squared plus c. So there are lots of questions and challenges now in how do we understand what kinds of objects live inside this moduli space. So before we tackle the moduli space, let's just look at some examples, just to get a concrete feel of what quadratic rational maps actually look like from the point of view of iterating. So I'm at liberty to choose my coordinates. I'm going to put one critical point at 0 and one critical point at infinity, and I'll suppose that maps to 1. Okay, a quadratic rational map has 2 critical points, and I'm going to use coordinates where one of those critical points is at 0 and one's at infinity. And then the image of infinity is 1. Okay, so then I can look at one such example, and it's given by this formula here. For this example, infinity maps to 1, and then 1 maps back to infinity, and then 0 maps wherever it maps, and then that point goes wherever it goes, and then that guy goes back to 0. So looking at this example, both critical points are periodic. So in fact, this is an example of a post-critically finite rational function of degree 2. The orbits of the critical points are finite. And let's have a look at what the shape of this rational map looks like. You'll notice that I have a Riemann sphere here. There's purple parts and there's yellow parts, and then there's the parts in between. These 2 points here you should think of as these points in the cycle of period 2. This is an attracting cycle of period 2, and every point in this picture that's colored pink has the property that under iteration, their orbit converges to this cycle of period 2. Every point in this picture that's colored yellow has the property that under iteration, it converges to this cycle of period 3, which you should think of as these 3 points. And then there are the points in between. That's called the Julius set of the rational function, which you could think of as the boundary of either the yellow or the purple region, or the topological closure of the repelling periodic cycles, if you'd like a definition. If you study this picture like Doherty and Hubbard did back in the early 1980s with a much worse picture, there's something that you can see in this picture about the shape of this rational function. It looks like something you've seen before. And that's what I'm really excited to show you next. This is one of my favorite parts of complex dynamics. So as I said, this map is post-critically finite. The forward orbits of the critical points are finite. And this map has pieces that look like a basilica, and it has pieces that look like a rabbit. There's a way to make precise what it means when I say that this quadratic rational function comes from polynomial parents. Okay. So in a very real sense, this quadratic rational map is the mating of a rabbit and a basilica. This is not my terminology again. Doherty and Hubbard. So this picture, which you just saw coming from that animation, the colors have been switched, sorry about that. But this picture, the last frame of that movie, is the dynamical picture from that rational function we started with. So let's figure out exactly what's happening here. So what's a mating? If you have 2 quadratic polynomials, I'm going to tell you how to build a rational function coming from them. I want you to take a topological 2-sphere. There it is. Look at the equator. If you cut along the equator and take the northern hemisphere and roll it out, you get a copy of the complex plane. Take your first polynomial, which in our example is the rabbit, and have it transform that copy of the complex plane. And then take the lower hemisphere and roll it out to a copy of the complex plane, and take the lower polynomial, which is the basilica in our example, and have it transform that copy of the complex plane. Then put these 2 complex planes back on the sphere. So you have a sphere wearing a northern hemisphere that's a copy of the complex plane, and a southern hemisphere that's a copy of the complex plane, and the northern copy is being transformed by the rabbit polynomial, and the southern copy is being transformed by the basilica polynomial. These two maps glue together to give you a ramified cover of the topological two-sphere. You might worry about what happens at the equator, but you don't need to. Why? From the point of view of the rabbit polynomial, the equator is near infinity. Near infinity, the rabbit polynomial looks like z squared. From the point of view of the basilica polynomial, the equator is at infinity. The basilica polynomial at infinity looks like z squared. So on the equator, you can define this ramified cover to essentially be z squared. You can do this precisely. That's called the topological mating of the two polynomials. And that's what's meant here with this picture, the topological mating. And then in that movie, you noticed that these two Julia sets were being stretched around the whole sphere, and there was a region in between the two Julia sets that was being squished. There's an annulus in the middle that's being collapsed in the movie that you're watching, and what's happening is we're taking a quotient, we're modding out by something called a ray equivalence relation, which I don't have time to define, but you should look at this picture. You're squishing this region. This is a ray here. I'm going to collapse this ray down to a single point, which will drag this point on the boundary of this Julia set to this point on the boundary of this Julia set and glue them together. So you mod out by that ray equivalence relation, and then you ask two questions. The first question is the quotient of that topological two-sphere, when you mod out by that ray equivalence relation and squish down this annulus, is that quotient homeomorphic to a topological two-sphere? If yes, is the induced map on the quotient topologically conjugate to a rational function? In this case, it would be of degree 2. If the answer is yes, then the polynomials are mateable, and the rational function that the induced map on the quotient is topologically conjugate to is called the geometric mating. So this is sort of a loose description of what it is. The best part about this is the movie. So let's see a couple more. All right, so let's watch the mating of the rabbit and the basilica again. So there's our rabbit, there's our basilica. We're squishing down this annulus in between them. We're gluing together the boundaries of these things. In this particular example, when you squish that annulus down, you do get something homeomorphic to a topological two-sphere, and the induced map on the quotient is topologically conjugate to that rational function. And that rational function is a mating. Let's look at some more examples. The mating of two rabbits. You have a purple rabbit, you have a yellow rabbit, put one on one side, one on the other, and you squish down this annulus in between the two rabbits when you take this equivalence relation. The quotient is homeomorphic to a sphere, and the induced map is in fact topologically conjugate to a rational map of degree 2. That rational map has two rabbit parents. One critical point will be periodic of period 3 in the yellow rabbit. The other critical point will be periodic of period 3 also in the purple rabbit. So this will give you a post-critically finite rational function of degree 2. It's the mating of two rabbits. This is super cool. This is the mating of two dendrites. Remember, dendrites have empty interior. So what is going to happen? You get a tennis ball at the end. Of course, what really happened is you got a space-filling curve. Those two dendrites were mateable, and so we take the quotient of this annular region in between, we get something homeomorphic to the sphere. The induced map on the quotient is topologically conjugate to a rational map of degree 2. That rational map has the property that the Julia set is the whole sphere. That's what you're getting. Okay, so those dendrites were mateable. Let's look at the mating of the rabbit and the airplane. And I have to admit that that's led to some pretty awkward conversations in public with co-authors. Looking at this movie, the rabbit and the airplane, looks like this procedure's working. The rabbit and the airplane are in fact mateable. You'll get a rational function of degree 2 in the last frame of the movie. Will be post-critically finite. One critical point will be periodic of period 3 coming from the rabbit parent. The other critical point will be periodic of period 3 coming from the airplane parent. All right, two basilicas. Doesn't quite work. This looks different from the other movies we've seen, and in fact it is. What goes wrong here is when you have a basilica on the top and a basilica on the bottom, when you try to take this equivalence relation and squish down the region in between, a loop forms like this. All of the points in that loop are going to be squished down to a single point, which means in the quotient, you're not going to get a sphere. You're going to get bubbling. So the quotient won't be homeomorphic to a sphere, and that's a problem. The basilica is not mateable with itself. Okay. There are other weird things that can happen, like one Julia set might eat the other one. That happens as well. Those two polynomials are not mateable either. So that was the rabbit and something called Coco-Copelli, which I didn't actually introduce you to. Alright, so those guys aren't mateable. So one question is, which polynomials are mateable? When can you get a rational function of degree 2 in this way from two polynomial parents? And this was studied, I think, in the 90s by these three mathematicians, Tonley, Mary Reese, and Mitsu Shishikura, using a very deep and centrally important theorem of Bill Thurston's called the topological characterization of rational functions, which applies to post-critically finite topological branch covers. They prove the following. If you take two quadratic polynomials, z squared plus c1 and z squared plus c2, we want to make sure they're post-critically finite. The orbit of the critical point is finite, so either the critical point is itself periodic or it's eventually periodic. Then the two polynomials are mateable if and only if those two parameters, C1 and C2, do not belong to conjugate limbs of the Mandelbrot set. What's a limb of the Mandelbrot set? The Mandelbrot set has this beautiful heart-shaped region called the main cardioid. Everything that is attached or growing from the main cardioid is a limb. So you can see that this is a limb. In fact, this limb contains the rabbit parameter. The rabbit lives right there. This is a limb here. This limb contains the basilica. The basilica lives right there. The co-rabbit lives in this limb right here. So conjugate limbs, this limb and this limb are conjugate limbs. So you, according to this theorem, cannot mate the rabbit with the co-rabbit, but you can mate the rabbit with the basilica. You can mate the rabbit with the airplane. You cannot mate the basilica with itself because it's in its own conjugate limb. So that's the mating criterion, which is a cool theorem. All right. So back to quadratic rational maps. How can we use polynomials and matings to possibly understand or help us understand this moduli space of quadratic rational maps, which is isomorphic to C2? Well, there are a couple of things we could do. We have a higher dimensional space, two complex dimensions. If we want to understand it, we could take one-dimensional slices of it. Now, hopefully I've convinced you in dynamics that if you want to understand the dynamics of your rational function, you should study the orbits of the critical points. A rational function of degree 2 has two critical points. So there are some interesting dynamical slices that I can take of C2 coming from imposing a condition on one of those critical points. Like, for example, maybe I want to carve out a sublocus of my C2, which consists of all quadratic rational maps where one critical point is periodic of period 47. That will give one algebraic condition. It will carve out a one-dimensional algebraic variety or an algebraic curve. And then I can study that one-dimensional object and try to understand it. So in fact, that's something very natural to do in this particular setting, and I'll call these the Milnor curves. So the Milnor curves inside the space of quadratic rational maps, the moduli space of quadratic rational maps, the Milnor curve of type Kn consists of all maps where F has a critical point that is pre-periodic of period K. So after K steps, the critical point is periodic of period N. So given K and N, I can try to study this one-dimensional object, study its geometry. What kind of Riemann surface is it? How many punctures does it have? Does it have any singular points? What kinds of maps live on it? What can I say about them? So these are very natural things to study. So for example, if you look at the Milnor curve V0n, K would be 0, which means after 0 steps, your critical point is periodic of period 1. That would mean that it's fixed. If you change coordinates and put that at infinity, this is just going to give you the slice of quadratic polynomials. And that's something we understand very well. So now let's look at its cousin, V02, this consists of all quadratic rational maps for which one critical point is periodic of period 2. Now, inside this space, you'll see lots and lots of interesting things. And in fact, if you study this carefully enough, and you sort of blur your vision like we did when we were looking at that picture of a quadratic rational map, there's a very precise sense in which this space is a mating of a mangled or modified Mandelbrot set piece, a black piece, and a blue basilica. The basilica comes from having one critical point periodic of period 2. And if you look at all the black points in this particular slice, they are in fact, from the point of view of dynamics, each rational function in the black is a mating of something with the basilica. So this is like I should be a little careful. I should say that's almost true. So this slice of quadratic rational maps has many, many matings inside of it, and the structure of this parameter space is in fact also a mating. And that's something that you can try to understand. And then I'll just briefly mention one conjecture and then I'll stop. This is the next one, V03, the set of quadratic rational maps where one critical point is periodic of period 3. You can try to study this the same way. Does this have anything to do with matings? It's actually much harder and more complicated. We don't know very much about these slices, and in fact, we would really like to know if they're even connected. So it's a big question in the entire subject. Are these Milnor curves connected? And one thing that we just proved over break is that in fact, some of them are. And that's the first time people have been able to say something about this. So what we proved is inside the moduli space of quadratic rational maps, if you look at the Riemann surface carved out by the condition that one critical point is eventually fixed, that's a connected curve. And tackling the other curves seems much harder in general. And sorry, I was a little quick there at the end, but I don't want to keep people. So thank you very much for your attention.
I'm sure you all thought it was worth it, but she took her whole time, so there's no time for questions. But she loves to talk about math, so come find Sarah and chat with her if you have questions. And thanks everybody for coming.
Thank you very much.